Now we will see an example for column design with bending. So what this problem is saying, it is saying determine the adequacy of a 15 feet long W12 72 column in a braced frame. It is a braced frame, so it is important to note to resist the a factored axial load of 200 kip. Axial load 200 kips and a factored moment of 100 kips and 65 kips about x-axis one and y-axis. The column is assumed to be pinned at both ends. So this is the column. It has axial load 200. It is factored. Yes, it is already factored. If it is not factored, you have to factor it. And then it has a factored moment about 100 keep feet or feet keep about x-axis, 65 feet keep about y-axis. So it has axial load, moment about x-axis, moment about y-axis. What is the length? 15 feet long. What is the section? Trial section is this. We should check whether this section is good or no. If it is not good, a larger section is required. Okay, so let us see what we did here. First of all, PU. This is PU. PU is known. If I go to the book, the column equation, this is the design equation. So first we have to choose whether we need this equation or this equation. How to find it? We need to find the ratio PU over PPN. PU is given 200. What is PPN? The capacity of this section. The capacity of this section using no moment. So we need to find KL. KL is 15 because K is on both ends pin. Or if it is not given, we assume both ends are pin. Now, if it is not, and if we know the support condition exactly, then we can find our K. You know how to find K. So based on KL from ASC manual, if you go there, you should get this number as they got it. I did not check this number, so it should be okay. So PPN is 736. Now if you do not find this value in the ASC manual, whatever you find, it should be very close. So you can use that. That is not a problem. Okay, so we found 736 and our PU is 200. Okay, now here is okay. Actually, we should not tell okay here because we should check for a moment. Then now which condition here? Still they did not decide, but again whatever decision we will see that, but we need to find this value. This is the moment capacity of the column about x-axis, moment capacity of the column about y-axis. So they are finding this value now. So now for Fy, what is our unbraced length? Unbraced length is 15. So our LB, where is our LB? LB they did not write. For this section they found in the ASC manual, that is LP is 10 feet, beam factor 5.59, LR is 37.4 feet. So our LB is in between these two, in between LB and LR. So in between, that means our capacity equation is PB minus beam factor LB minus LP. This equation to me is not correct because there will be phi here. There is a CB. They assumed CB1, but there should be a beam P here. There should be a P here. Maybe in the ASC manual the combined value is 5.59. PBF is 5.59. Maybe they made mistake here. So whatever it is, whatever you find, so this is 405 mpx minus PBF minus LB minus LP. So they found 380. 380 is our design moment capacity about x-axis. Now we will find the capacity about y-axis. Why do we need to find y-axis? This one. What is the equation? It is z phi zy fy or 1.5 phi sy fy. In the new division it is 1.6. Whatever addition you use, find this value. Zy sy both can be found in ASC manual. So they found in this side 184, in this side 182. So we will consider 182. Now again to go back here, maybe they made a mistake. There will be a phi here. There will be phi here, and they found this value. So if yes, in the ASC manual you should get PBF directly. Now whatever you learn, use your own understanding. So that is the only mistake so far I found. It's not a mistake. Maybe in the old version of the ASC they might use this format. Okay, something else also, they did not use CB here, CB, because mostly we consider on. Okay, so again to revise you, we got this value, we got this value. Now we have to find this value and this value. To find this value we need to find b1, and whatever b1 times 100 is mux. This is b1 times 65 will be muy. Okay, so how to find b1 and b2? We know that this is the equation 0.6 minus 0.4 m1 minus m2, but conservatively we can use both. For both cmx or y, whatever direction is, we can use 0.885. It is not the multiplication, it says cmx and cmy both, they are 0.85, they are using this. Again we need to find Euler load about x-axis, Euler load about y-axis. Why? Because to find b on x is cmx over 1 minus pu, Euler load about x. Same thing, b1y cmy divided by 1 minus pu over p1y. So we need to find both Euler load about both axes. So they found pi square ea, everything is clear, kl over rx, and here kl over ry. So they found this value 5255 1723 keeps. You will get the same number. There is not so many factor here, same number. Now after that after that they found your b1x. After calculation they found 0.88, but we cannot decrease it, we cannot use less than 1, so we have to use 1 here. b1y they found here 0.96, but we cannot use 0.96, we have to use 1. So for both cases they used 1. Then mux b1, whatever moment given 100 is 100, keep it. muy, whatever they found b1 1 times 65. So now we know all the parameters. Now which equation to use? It depends on the ratio of pu over ppn, and pu given 200, ppn calculated 736, we got 27, that means more than 2, more than or equal to 0.2. That means our first equation. So they inserted all the value, 89, this is the moment, this is the moment capacity about x-axis, moment capacity about x-axis, and they found 0.82, which is less than 1. Less than 1, if you go to book, less than 1 or equal 1, that means this column is good. So this column is good. Now something to note from this example is cmx cmy we will use 0.85 to be safe, number 1. Number 2, we saw that what else? We saw that b1 and b1x b1y, it cannot be less than 1. Less than 1 means we are decreasing our calculated moment, which we cannot. So at least 1. That is second thing. Third thing is that this equation, in this equation they missed p here and a combined cb. If I write the equation for this case, it was this. So capacity, now if our lp greater than lb lr, if this is lp, if this is the case, our capacity, we saw cb p mp minus p bf, then lb minus lp. That is the equation for this condition. Now this value we can use on this value, we can find AISC manual, this value also manual, this value is our arm base length, it is from manual. So this is the correct equation, but mostly by BF they mean the whole thing, so it may be possible. Now this value you should not memorize, or you should not be stick to it, because with time it changes, because the coefficient changes. So hopefully you understood the example. Something else in this example too. Example, so this column is about comprehension. This load factor axial load 200. If they say this load is tension, moment remains the same, what will happen? So column may take tension also. What is the change? The only change will be, we do not need to worry about b on x or b on y. So whatever moment is given, that is the moment, because for tension there is no buckling. So again to remind you, so for tension, if I draw here, if it is tension, if load is given in tension, whatever your moment, that doesn't matter. If it is a tension, load, b1 is on x or y, whatever is, or simply do not worry about beyond. Just whatever your moment given, that is done. Whatever your moment given, that is done, and everything else will remain the same. Only do not worry about beyond x. As you should not worry about beyond x, you should not worry about cm, you should not worry about the buckling load, or x or y, whatever, you should not be worry about it. Discard this, simply b1 is on. Okay, thank you. We will see another example in the next video.